Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to take a look at what is called the orthogonality of the four subspaces. So let's write that down. The orthogonality, big word, of the four subspaces. And if you recall the four subspaces, well, we're going to find them in a moment, but there's the column space of the matrix A, there's the null space of the matrix A, there's the row space, which is the column space of its transpose, and then there's the null space of A transpose. And those make, or the left null space as it's also called, those make up our four subspaces. So first off, we've got this huge word, and it's called orthogonality. And what orthogonality means is this. If, let's see, let x, y be just any vectors in any dimension are n, then x and y, it's the vector x, and y won't. X and y are orthogonal, when x dotted with y equals 0. Well, what is that? We've said that before, but we didn't use that big word. Instead, we just called it perpendicular. And that's what it means. And another way of saying that, as we'll write it down here, kind of save my space, is we could say that the inner product, in other words, x transposed y is 0. And if you recall, this was called the inner product. Okay, and this is something that we've seen before, and actually we proved at the beginning of our semester. Say I have some vector here, x, of some vector x, and I have another vector here, y. Well, then this would be the vector here. Right? Maybe you'll do it in a different color. How's that? Let's use a different color. Then if I subtract the vectors, I would have the vector, this would be the vector of y minus x. Well, and then what we can say then is that the length of x squared plus the length of y squared is equal to the length of y minus x squared. Now, that's what orthogonality means. So this is orthogonality of just two simple vectors. But now what we want to do is, what about, oops, let me bring this up here. What about orthogonality, Okay, that's a long word to write. So I think for now we're just going to use this upside down T that stands for perpendicular. So what about orthogonality of spaces? What about orthogonality of spaces? Well, I want to point this out because it's a little bit more delicate than you might have thought. Because say you're just sitting here in your room. You probably are sitting in a room right now as you're watching this video. And your room probably has a wall. Maybe it looks like this. And maybe it has another wall that looks something like this. And then maybe there's even you sitting out here, out there on the floor. Or maybe you have your favorite chair or something like this. Well, it's easy to think of the walls. We say our walls are square or they're perpendicular to each other. But let's really be careful about that. So when we say that, we're talking about a vector. We're talking about it if we think of it like this. So those two vectors, if your house was built square, then those two vectors would be perpendicular to each other. But my question, though, is the space perpendicular to every vector in the space perpendicular to every other vector in that space. Well, let's try this. What if, let's just use this as our origin, where the two walls and the floor all meet. What if my vector just comes barely out on that left wall, and maybe just comes barely off onto the floor like this? Those are not perpendicular. As a matter of fact, the angle between them would just be this little angle here. And we've already learned how to use the law of cosines and the dot product of vectors to find that angle theta between those two vectors. So when you think about a room, even though your wall is square to your floor, those aren't orthogonal spaces. So let's take a look at an example. We're going to look, and then we'll try it for the general case. So what we're going to do is this. We're going to find the four subspaces. Find the four subspaces of A equal, let's use 1, 0, 0, 2, 0, 0. Okay, there it is. That's our matrix A. And I make mistakes, so just because we're going to need it, I'm going to write A transpose down as well. So row 1 becomes column 1 becomes row 1. So 1, 0, 0. And then column 2 becomes row 2. So those are my two matrices. Well, you can look at A and you can tell right away that it's going to be of rank 1. Rank 1. So let's see, A has a null space, and I'm going to do this kind of quickly. The null space of A is going to be x2 is our free variable. So we're going to have a -2 and then a 1. So that should be my null space. And then my column space, so there's my null, and we'll find this for the other vectors as well. What about A transpose? Let's find the null space of the transpose. It wouldn't be x, it's probably y. So y, the null space here is going to be, if you take A transpose and row reduce it, you just have a row of, you have the row with 1, 0, 0, and a row of zeros below it. So your null space is just going to be, an x2 is going to be free, x3 is going to be free, your pivot variable x1 is going to be 0, so you're going to have x2 is going to be 0, 1, 0, plus, oops, not x2, that should be a y2. Let me fix that. Plus y3, which again, the pivot variable is 0. There is no y2 in the y3 component, and then a 1. And there we have it. Now we can write our four subspaces. So let's write our four subspaces. And then we might have to take them and put them on the other space here. So the column space of A, well, that's just the vector. I'm not even going to use an equal. Let's just use this is defined as, it's the linear combinations of 1, 0, 0. Okay. Then my column space of A transposed is the vector 1, 2. And then I can say that the null space of A is defined by the vectors -2, 1. And our last one is the null space, I'm going to bring it down here, the null space of A transposed is defined by the, oops, not equal, it's just defined by, or it's the span of the vectors 0, 1, 0, and then the vector 0, 0, 1. Okay, so this should be review. Hopefully that was a good review. If I went a little fast, stop the video, take a moment, please check my calculations. Now we're going to go on. And I picked this example because we can draw these pictures. And so that's what we're going to do next. So I'm going to bring up a new screen. You don't have to get a new piece of paper unless yours is full. And so here we go. Let's draw this. So I might have to bring this back up for a bit, but I'm going to take this down. Okay, here we go. So the column space of A, we said was defined by the vector 1, 2. So let me just draw this. So here's oops, that's not going to work. It's a little off my screen. So how about this? This is R2. Okay, this is R2, and in R2 is the column space of A, and the column space of A is the set of vectors defined by 1, 2. So 1 and 2. So let's see. Let's draw that in. So that's going to be right there. So I'm going to turn my tablet here so I can get a nice line. And look at that. Oh, that just looks good. Now we also need another set. Our null space of A is also in R2. So this is what I just drew here. This is the column space of A transpose, which is the row space. And then we need to draw in our, let's put in our null space of A. That's defined, we said, by the vector -2, 1. So I'm going to put my couple more tick marks over here, -2, 1. And then null spaces, I think, are best done in a bright yellowy green color. So how about this? There we go, and that is a fine looking null space. Okay, that yellow, or greenish yellow, that's the null space of A. Okay, now let's draw this next one. This next one's going to be a little more interesting. You're going to have to bear with me. I'll do my best. So the null space, the column space, and the null space of the transpose, these are in R3. Well, this is a picture we've practiced before, so let's give it our best shot. So you're going to have a vertical axis, then you're going to have your y-axis, maybe about like that, and then we'll also have an x-axis, about like that. So I'll label these z, y, and x. Okay, now this is interesting here. The column space, now I'm going to use some colors here again. Let's use, I've got this beautiful pink color. The column space is the vector 1, 0, 0. Well, oh goodness, I labeled as z. That should be an x. Okay, now the column space is that right there. That vector. In other words, the x-axis is my column space. Now, let's see what else we have here. So notice this. So if I wanted to graph my null space of the transpose, that's the vector 0, 1, 0. Well, that's this vector maybe like right here. And then the other vector is 0, 0, 1. That's just a vector along the z-axis. Wait a minute. The null space of the transpose, that's going to be the y-z plane. Yes, it's this whole space in here. This whole space in there. Well, let's see what we've got here. So let me label those so we got those nailed down. Our pink vector here, this is the column space of A. And our yellow kind of maze-looking piece, this is the null space of the transpose. Now, let's go back to the title, the opening idea, and that is this. That is that couple things. First, this is important. Let me write these down. I got so many ideas going, it's hard to stop myself. First, notice that the column space of the transpose, or the row space, and the null space of A form a basis. Form a basis for Rn, which in this case is R2, or R2 in this example. And similarly, or probably I should say similarly, but we'll just go and similarly, the null space of the transpose, the null space of transpose and the column space form a basis for Rm, or in this case R3 in this case. Okay, and the idea is that the dimension of the null space of A was 1. The dimension of the row space is 1. Those two numbers should add to the total dimension of the space. Similarly, the column space is dimension 1 because there's one vector in the basis. The null space of the transpose has two vectors in its basis. So 2 plus 1 is 3, and that does cover all of R3. Now, here we go. Here's the big moment. I want to show you, that, and you may be able to see this, but I want to show you that this is true. I want to show you that, what do I want to do? Show that the null space of A is orthogonal to the column space of the transpose. Well, now we're going to just do this initially for a single specific example. We'll take a look at the general here soon enough. So what is that going to look like? Well, let's just take anything in the null space of A. Well, the null space of A was defined by the vector x null is just some scalar A times, we said it was minus 2, 1. Okay, so in other words, the null space is the line of minus 2a, 1a. Okay, now then the column space of A, I'll put it, XR, the column space of A transpose, I'm going to call it XR for X in the row space. That is just some scalar B times the vector of 1, 2, and so we'll just write this as B and 2B. B or not to be. All right, if these are perpendicular, this should equal 0. Let's find out. So, in other words, is X null transposed XR, what do they equal? Let's find out. Well, this is the vector of minus 2a, 1a, that's X null transposed, times XR, that's B and 2b. Well, if we multiply these together, this is going to be a minus 2ab plus a 2ab, and sure enough, that's 0. That's 0. Now let's do this again. Now let's show that the null space of A transposed is orthogonal to the column space of A. Okay? So let's take some B. That's usually what we'd represent it as. So B is some scalar, we'll just call it A, times the vector 1, 0, 0. Well, I'm just going to use my B then as just A, 0, 0. Okay? And then let's take our so this was B, this is B is in the column space of A. And then let's take our Y in the null space of the transpose. I know I switched those orders, sorry about that. It's just, It's commutative. Sorry, that was a silly math joke. So y in the null space is going to be some scalar. Let's call it like d. It's going to be d times 0, 1, 0 plus some other scalar, maybe c times 0, 0, 1. Well, let's just write that as the vector 0d0 and the vector 0, 0, c. Well, this says then, I've got just enough space here, I think. This says that B transposed y, well, this means B has to be times both of those. So this is going to be B transpose. This is A, 0, 0, times the y. Well, I have two vectors. I have the vector 0, d, 0. Whoops. And the vector 0, 0, c. And you can quickly see that a times 0 is 0 plus 0 times d plus 0 times 0. This is going to give me 0, and the second vector 0 as well. So what did we just find? We just found that for our specific example, we found that the row space of A is perpendicular to the null space of A, and that the column space of A is perpendicular or orthogonal to the left null space. Okay. I think we'll stop there, and in the next example, we are going to take a look and prove this for the general case. All right, hope that helps. Thanks for watching.